The following podcast is sponsored by Structure Tech.
So on today's episode, we're going to dig into some technical talk, and specifically, we're going to dig into the topic of electricity. Welcome, everyone. You're listening to Structure Talk, a Structure Tech presentation. My name is Bill Ulrich, alongside Tessa Murray and Reuben Saltzman. As always, your three-legged stool, coming to you from the Northland, talking about all things houses, home inspections, and any other topics that might tickle our fancy on a given day. Exhale, okay? Just go. We have spent the last 4 episodes talking about things like business and the market, and we haven't really gotten into any technical conversation. I think Reuben's breaking out into hives. I think he needs to have some technical talk.
We do. We got to have a good mix of that.
Yeah. So on today's episode, we're going to dig into some technical talk, and specifically, we're going to dig into the topic of electricity, because we all understand electricity. It's like super simple words like grounding and bonding and earth, and what's the difference between the earth and the ground, and all these kinds of things. And Tessa has volunteered to explain it succinctly for anybody who's listening to this podcast.
Gosh, no pressure.
So tell everybody why we're talking about electricity right now.
Well, we were trying to think about technical topics to discuss, and Reuben was like, is there anything that's fresh in your mind that you've been working with the recent group of trainees with? And we just covered electricity this week, and we're focusing on kind of one system at a time. And I think that out of all the different systems we cover, the electrical system is probably the most confusing, and I think the most intimidating for people. Sometimes it's plumbing, sometimes it's HVAC, but everybody can agree electricity can be a little confusing, and it can also be just downright scary. It's like the one area that if you're not being careful, like it could kill you. So there's reason for people to have a little bit of trepidation around electricity.
So have either of you ever been shocked, like really hit hard?
No, I'm knocking on wood right now. No, I've had a really close call, but I have not been shocked really. I mean, I've had little shocks here and there, but nothing that like threw me across the room or anything like that.
Yeah, I've never been shocked where I got thrown across the room, but getting shocked, painful shocks, probably at least a dozen times. That might tell you something.
That explains a lot.
I think the first one was probably, 5 or 6 years old, just plugging in a lamp where I had my finger on the prong. I remember there was another one where I don't remember if I got shocked or not, but I like to mess around. And my dad being a carpenter, he always had a garage full of miscellaneous stuff. It's like, oh, there's the electrical box, wires and plugs and all this. And I took one of the plugs, and I don't know how I knew how to do this, but it was a plug and it was an extension cord. And I cut the end off and I stripped the wires back, and then I connected the 2 wires to each other. So you just got the hot and the neutral connected, and I connected them with a wire nut, and then I went and plugged it in. And
oh my gosh, you would do this, Reuben. Oh my gosh.
Yeah, I just want to know what happened. It was just a huge flash. I remember I had soot, it was like a carbon flash, and I had black soot all over my hand. Scared the heck out of me, and I very worried about how much trouble I would be in, and I had to wash my hands really good, not tell anybody, and put it all back. I'm sure my dad was like, why is this circuit breaker trip? So I've done a lot of tinkering.
Oh, God.
Well, I'm sure you've seen your share of odd setups in basements of old houses in probably Minneapolis, not St. Paul, because we don't do weird things like that, but mostly Minneapolis.
Right.
I remember one day I walked in our oldest son's room, and he had a tendency to take things apart and strip back wires. And there was an extension cord that he must have wanted to use, that he just peeled it back. He took the ends off and he jammed it in the outlet, and it worked fine for he had like 2 computers and something else plugged into it. Oh my God.
That's the stupid thing about electricity, is you can get it so horribly wrong, but it'll still work.
Right. Yeah. Scary.
So how are the trainees feeling about electricity?
Well, some of them were more comfortable than others, I think, coming into it, kind of just different experience levels. But There was one topic which I think seems to confuse people across the board. And I'll even say, like, I still get confused about it too. And having to put the training curriculum together, I really spent a lot of time reading about this subject because I didn't understand it, is what I found out. And what I'm talking about is grounding versus bonding and why we have it, what it means, what it does, and the difference between it.
Okay. Can you expand on your newfound knowledge?
Well, disclaimer here, I am not an electrician. I am just a home inspector. So I'm going to give this my best shot. And I'm sure we'll have much more knowledgeable people listening to this than I am on the topic. And please feel free to write in, let us know how we're wrong, how I'm wrong in this area, but I'll give it my best shot. So one thing I think that's really interesting is that electricity will take all available pathways to get back to its source. And I think a lot of people think that the earth is its source, but that's not necessarily true. That could be true if we're talking about lightning, but in a lot of other situations, source means the electrical panel, which is then connected back to the transformer where the electricity comes from and then gets distributed into your house. And so just understanding that electricity will take all available pathways. However, it'll have the most voltage on the path of least resistance, if that makes sense.
Yeah.
So if there's a lot of good conduction, you'll get a lot of electricity.
In direct proportion to how much resistance that path has.
Thank you. Yes, exactly. Yeah. So we've got bonding and we've got grounding, and they do two different things, these two different systems. And really, grounding is talking about a pathway to the ground, which means to the earth. Those terms can be used interchangeably. And why you would want that is so that if there is, let's say, if lightning strikes your house, and there's all this electricity, it's got to go somewhere and it wants to go back to source. You need to have a pathway to the earth for that, to dissipate all that electricity so that you don't cause fires and fry everything in your house. But what's really, really important is that all the metal components in your house are connected together so that if there's any extra electricity or stray electricity, like static or a surge in voltage or something like that, the electricity can find a pathway back to source, like the electrical panel. And the electrical panel has safety measures built in to protect people and appliances from being electrocuted and appliances from being just blown up. And so we've got circuit breakers or fuses that will trip or blow if there's extra voltage going through a pathway that shouldn't have that. Does that make sense? Was what I'm saying making sense?
Yeah. And so why do we have that third prong on outlets? It brings us to the ground plug, we always call it. Really shouldn't be a ground plug, right?
That ground pathway, I mean, we use the term ground, but really the purpose of that is if there is stray voltage, either through, let's say you have a hot wire in a circuit and that wire comes loose and it comes in contact with metal housing on a light fixture, you want to have a ground wire so that that stray electricity has a pathway back to the source, back to the panel, so that breaker will trip. If you don't have that ground pathway back to the panel and you don't have a breaker that will trip, then that light fixture could just be silently energized, carrying that current, and no one would know. And they can touch that light fixture and someone could get electrocuted depending on what they're touching and if they're an easy pathway or not.
So that was my question. They become a pathway. And if they, as a person, are a better pathway than the housing, let's just say there is a wire hooked to the housing, but it's not hooked well. If they're a better path, then they could potentially get shocked.
Yeah. And this was interesting. Reuben, I remember listening into a class you're teaching to real estate agents about the difference between electrocution versus shock. That was something that was new to me. I didn't understand the difference. Do you want to explain that?
Sure. To make it really simple, you don't ever get to tell someone that you got electrocuted because you're dead. That's it. Anyone who tells you I got electrocuted, you don't need to correct them, but you mean you got shocked. That's really what it means. A shock, you don't die. That's it. Plain and simple. I suppose there could be an exception if you get resuscitated.
So in that example, for instance, one location we always check for to make sure that light fixtures are grounded is above like sinks, like in a bathroom or in a kitchen.
Exactly.
Because explain why, Reuben, why that's so important.
Well, if you had one of the wires just accidentally short out with the housing of that metallic fixture, it's exactly what you said, Tess. It would be silently energized. And if you're standing in your kitchen, you've got wood floors and you've got shoes on and socks on and all that, and you touch that energized fixture, it's going to give you a shock. I mean, you're going to feel it. It's going to hurt. But if you think about where that current is going, it's going to travel through your body and then your socks and your shoes and the wood flooring and all this other stuff in the house. It doesn't have an easy time traveling through all these things. I mean, those are all pretty good insulators. And even with all that, you'll still get a painful shock, but it won't be enough to kill you. You won't get electrocuted. But let's say you're standing at the kitchen sink, you touch that same light fixture, and you happen to be holding your metal faucet at the same time. Well, what's the pathway there? Let's think about it. Your metal faucet is going to be connected to metal pipes, and those get directly bonded. Those are connected directly to the electrical panel, so they have a very good path back to the earth. And you touch that same light, you'd probably get electrocuted. I mean, traditional 120 volt wiring is a very deadly current. People talk about 240 being super deadly, but it's not more deadly than 120. 120 is very disruptive to the human heart. So that's why it's so much more dangerous to have ungrounded fixtures right next to plumbing fixtures. And especially if your hand's wet, it makes it an even better conductor.
Can I ask this question? You mentioned a specific thing in that explanation, Reuben. You said that metal pipe will be bonded. What if it's not bonded? Will that current will go probably to the earth? It'll eventually, maybe connect up to the earth that's below your house or something like that. Maybe it doesn't get back to the panel. It just goes to the earth. Is that a more dangerous situation than sending it back to the panel?
Yes. Sorry, Reuben. I'm going to jump in here.
Yeah.
You want that electricity to go back to the current and complete the circuit so that the circuit breaker can trip and do its job so that you don't get electrocuted.
In the situation you're describing, Bill, if it wasn't properly bonded and someone accidentally had an energized wire come in contact with that metal piping, you could quietly energize all of the metallic fixtures in your house. All of your faucets, all that stuff could all be energized, which would be extremely dangerous. We can't have that.
Yeah.
And the way you prevent it from happening is you connect it to your panel. So if a hot wire touches it, there's such a good path going back there that's going to overload the circuit breaker. That's the whole idea.
It pops in an instant, and hopefully that instant is a short enough period of time that you don't take enough of a shock to.
Right. You'll be shocked, but you won't be electrocuted.
Yes.
Okay.
So bonding, the importance of bonding is so that all of these metal components in your house that could carry a current will carry that current back to the panel so that you don't potentially get electrocuted if something were to short out or a wire came in contact with that. So, our metal water piping, our metal gas piping, phone service, phone lines, all these things, water softeners, anytime there's metal components, they need to be bonded.
Yep. If you want an example of what that looks like, a really common one would be you go down to your water meter down in the basement, wherever your main water shutoff is. Someone should be able to remove that water meter and you'd still have all of your metal water piping, assuming you've got an older house. Newer houses, we got a lot of plastic piping, but older homes, you've got a lot of metallic water piping. You should be able to remove that meter and still have everything connected. And they do that by running a wire from one side of the meter over to the other. And they got these big metal clamps, and it makes sure that it's all at the same electrical potential. And that's why we're doing it.
Jumper wire is like another name for that you hear a lot of times.
Yeah, exactly.
Is a newer house less dangerous because there's less metal in the plumbing system?
That's a good question, Bill. I guess you don't have to worry about your water piping being silently energized, potentially, if it pecks. But
if the water that were in those pipes was in contact with electricity, it could potentially...
Yeah, potentially.
I'm asking questions kind of looking with my
I was
eyebrows.
just thinking, there's another thing, think about ductwork in houses, and it's all metal. And actually, we had an inspector on our team too. We won't mention names, but that very thing happened where wasn't there a wire that shorted out and came in contact with some metal ductwork in a basement?
Yep.
And it silently energized it because it wasn't bonded. Our inspector was walking through, touched the ductwork, and got a really good shock, right?
Yeah, it had happened like twice. I think it happened once where he did the initial home inspection and he found that there was a problem with it. And then he had touched it and he got a little tingle. He's like, there's a problem here. And then when he went back, I can't remember all the details, but somehow he had accidentally touched it or purposefully touched it, and he had socks on this time.
Instead of his shoes?
Instead of
He
his
took his shoes
shoes.
off?
And, hot summer day or whatever, you might have kind of some sweaty socks. You're standing on the concrete floor. All of a sudden, that same shock was way different because he had a very good path back to the earth.
Wow.
And that was a nasty shock. It all depends on what else you're touching that affects the severity of your shock and whether you live or not. Yeah.
Wow.
So that brings us to GFCI devices, ground fault circuit interrupters. They've been around for, I think, almost 50 years now, maybe even longer.
Since the 70s, right?
Yeah. And it's those devices that, it's an outlet that has a test button and a reset button. The whole idea there is to keep people from getting electrocuted. They're life safety devices. And those sense when the current isn't going back to the panel through the wire. If it takes some other path, like using the building or using you, whatever it is, they sense that there's some current leaking out and they cut it off. And it doesn't mean you don't get shocked. You will still get shocked. That's what it takes to set these things off. But hopefully it's going to cut that circuit off before you get electrocuted. And what's the threshold there, Tessa?
Oh, gosh.
I'm testing you here.
Yeah, I have no idea. I wish I could answer that, and I probably should be able to answer that, but I can't.
I thought it was like, not like the number really matters, but I thought it was like 0.05 milliamps or something.
Okay. So it's really sensitive.
And, I can't remember where I saw this. I thought it was some of the training material that you had put together, but I found it interesting that there's different thresholds for electrocution for men and women.
Oh, yeah. That was interesting. That actually, I know what you're referring to, Reuben. And as I was doing my research, I came across something on the internet from Mike Holt. Yeah, there are different limits for men versus women on kind of that electrocution threshold. But really, it came from a study that was done a long time ago. I don't know the exact year, but before the 1950s. And apparently they had a bunch of men in one room and hooked them up and basically gave them little shocks and increased it until they couldn't hold on to something anymore and they had to let go. And they were measuring that threshold, and they did the same thing to women. But what was interesting is he was talking about in this study is that the men's limit was higher, probably because of the peer pressure of being able to hold on to that longer, because all the men are standing there watching you and they're going to be laughing at you if you let go, versus the women were like, this hurts, I'm going to let go. And there was no pressure.
Yeah, this is okay. So this is junk.
So yeah, take it with a grain of salt. If we redid that study today, I bet, it's very similar, I'm sure, in all humans. Yeah.
It reminds me, Mythbusters did something on who can tolerate pain better, men or women. And the study they did was they'd have people hold their hand in a bucket of ice water and see how long they could do it for. And it was the women. The women had a much higher pain threshold. I found that interesting. I tried it just to see how well I could do. And I could, a few seconds, everybody beat me on that one. And I thought, I've thought I've had a pretty high pain threshold, but then I thought, well, I've had frostbite in the past. That might make a difference too. So who knows? It's so many variables.
Yeah. Well, I think there is some biology behind, women's pain threshold being greater than men, obviously.
I think this has been solved, for hundreds of years. Yes, because of the childbirth. But I mean, I know some people in the medical industry and they deal with men and they laugh because they're ladies and they laugh because he was such a wimp about pain, and we go through childbirth and it's part of everyday life for us.
My wife is an ER nurse and she says the same thing. The men are the worst.
They're worse because they're trying to outsmart their buddies or out tough their buddies. But I mean, if the smarter species drops the electric wire first, I mean, I can take it longer than you can. Okay, you win for being the biggest dummy.
Back to GFCI. So I was just going to say, Reuben, I mean, you talked about the outlets that have the test reset button on them, but for a lot of homeowners that we're doing inspections for, there's other ways circuits can be protected with a GFCI that's not just the outlet that has the test reset button on it, right?
Yeah.
Talk about those other methods.
Well, you could have, I mean, this is what you typically have in kitchens, is where you're going to have one or two outlets that are GFI outlets, and then you wire all the rest of the outlets downstream from those. So you have the equivalent level of protection at all of those outlets, but they're not actually GFCI outlets. And to verify that, most home inspectors carry around these cheap little $7 testers, stick it in the receptacle, you press the button on top, it's a GFI tester, and it will remotely trip that outlet. So it's a way of verifying that the outlet is wired downstream from a GFI outlet. It's GFI protected, we call it. Another way to do it is you could have a GFI breaker. Same principle. The breaker protects everything on the circuit. However, if you have an older home and you've got a bunch of 2-prong outlets throughout your house and you want to upgrade those to 3-prong outlets, of course, the best way to do that is to run a wire from the panel all the way to the outlet. Or if you have metal conduit that could serve as a good conductor, you could rely on that. And you actually have a good path going all the way back. But if that's not available, it's actually acceptable to just have GFCI protection for that outlet. You can install a 3-prong outlet. That 3rd prong connects to nothing, and it's still acceptable to do this. You just need to make sure that it's GFI protected. So that's a way of kind of getting around doing a lot of extra work. The one caveat here is that if I, as the home inspector, go up to this outlet, I stick my tester in, it's going to tell me the outlet's not grounded. I can figure that out. But then if I press my GFI test button, it's not going to trip that remote GFI, because all it's doing is it's touching the neutral and the ground circuits wires together. And that's what trips it remotely. And if you don't have a ground wire, it can't trip that other thing remotely. So a home inspector might incorrectly say it's not GFI protected. This is a defect. It's a hazard. Fix it. When in reality, it's not. And in those cases, the only way a home inspector is going to know it for sure is they track down that GFI outlet, and who knows where it's going to be, but you got to track it down, press the test button on there, and then go back and check the outlet again and make sure the power's off. So it's kind of a pain in the butt.
Have you taken GFCIs apart to see what the actual mechanism inside that outlet is?
No, but I've looked at pictures and diagrams. If I remember right, it's just something, I think it's a little magnet in there or something. No, Bill, I have no idea what's...
I'm surprised you take everything apart, right? Like I was going to ask you if you took that cheapo outlet tester or inexpensive outlet tester apart to see what makes that thing happen, or what makes that thing
sense an upcoming video blog.
Oh, no, I've got pictures. I'll show you. I can post. Yes, I've done that.
Well, so what's the difference then, Reuben, between an AFCI and a GFCI?
Well, the AFCIs are designed to prevent fires. That's essentially it. A ground fault prevents people from getting electrocuted. Arc fault prevents fires. It's going to sense when you have current that has this irregular signature, if it's going to be arcing or glowing, causing a wire to really heat up. It's got this black magic inside the breaker that senses that, and it prevents fires. That's as much as I know.
So for instance, like if someone was hanging a picture on the wall and the nail nicked a wire, that breaker would sense kind of that leak in the current and it would trip the breaker?
That's right. That's right. And I mean, if you just had a complete dead short where the hot wire and the neutral wire just touched each other, any old breaker is going to get overloaded instantaneously and trip. But it's where it's just touching a little bit. It's kind of a high resistance connection, not enough to overload the breaker, but enough to make something get really hot and start on fire. That's where the arc fault breakers come in.
So are arc fault breakers an acceptable safety measure when you've got a house that has knob and tube wiring? Because we have a lot of knob and tube wiring here in the Twin Cities.
I would defer to the insurance company and say, hey, you guys have a problem with this house. What if we have arc fault breakers? I've never asked of this, but I'm pretty sure the answer is going to be, you got what? Huh? Yeah, whatever. Don't care. And as far as actual safety goes, we know there's nothing inherently unsafe about knob and tube wiring. I mean, the wire itself is okay as long as it's all properly installed and nobody's messed with it and it hasn't been damaged. But if it's been damaged and people messed with it, it's like, I don't care if you had arc fault. That's not an excuse for all these other defects. So our arc faults will surely make it safer. I'm not saying don't add arc faults, but that's not going to make an unsafe situation safe.
Tessa, when everybody left your class for the day, that kind of deep dive into electricity, were they feeling pretty confident?
I wish I could say that. There's a lot of ground that we cover at this point when we focus on one system and we cover it all in one day so that they can get out into the field and see these things with our field trainer, Neil. I think some people probably had a little bit more experience than others with just electrical systems. But one thing is true. I think just the idea of grounding and bonding was something that they, even if they thought they understood it, once we kind of talked through it, they realized, oh, maybe I didn't really understand it.
It's the way I felt when I picked up the book, the greatest book of all time, when you want to learn about electricity in a short time.
Inspections of existing dwellings.
Yes.
Yeah.
Electrical inspections of existing dwellings.
Yeah.
it's a fascinating book. I mean, technical, and you got to take it in very small bites, or at least I had to, but fantastic book.
Yeah, for sure. One thing that is still to this day, I don't know if I could explain it very well. And Reuben, I'm putting you on the spot.
Oh,
but so on your standard 120, 240 volt service to a house, you'll have 3 wires and you'll have 2 hots and a neutral, right?
Mm-hmm. I'm with you so far. I understand that. Yes.
Part of the inspection process is if we've got, an overhead service to a house, is making sure those wires are in okay condition and the masthead is okay and there's a drip loop and we've got, insulation over the clamps where we've got the transition from, the utility owned portion of that line to masthead to homeowner portion. How come the 2 hot wires need to have the insulation over the clamps, but the neutral wire doesn't need that? If neutral wires can carry a current back to the transformer in a situation, they can carry current.
Yeah, the neutral wire surely will carry current. I mean, the only time that neutral wire doesn't have current on it is when you have the exact same load on the 2 ungrounded or the 2 hot conductors, or you have 0 load on those 2. Anytime there's any kind of imbalance, that neutral picks up the rest of it. And it's safe to say there's an imbalance pretty much 100% of the time. So there's always current going back on that. But if you were to just reach up and touch that bare neutral, you're not going to get a shock because it's at the same potential as the earth. It's grounded.
I'm just processing that.
Tessa's looking out her window right now with a very thoughtful look on her face.
Okay. And it makes sense because when you say grounded, that overhead service goes into the main panel. Then we've got our grounding electrode conductor, which is a bare metal wire that goes from the panel into the earth, basically. And it's tied to either maybe some rebar coming up through the foundation or metal water piping or metal rod outside the house, or 2 of those options, most likely. So that's the pathway back to the earth, you're saying. That's why it's the same potential as the earth.
That's right.
Because of that whole connection.
Hot wires are only dangerous to us because that neutral wire is connected to the ground. And so we're always kind of completing that circuit. If we didn't do that, then you could actually touch a hot wire and you wouldn't get shocked.
Okay. Yeah. See, electricity is confusing.
Yes. Now, one thing that is scary, and we found this on a couple of home inspections, is where you have that neutral wire disconnected or broken or cut. However you want to say it, it's not completing the circuit. We've found that on a few houses. And in that case, if you were to grab one end of the neutral in one hand and one in the other, you would get electrocuted. So that would be dangerous. If you're in a house and you've got like some of your lights that are flickering and they're getting really bright or really dim and you're seeing all this crazy stuff in your house, there's a good chance you got a problem with your neutral wire. Either it's damaged or it's completely cut, because that whole circuit will get completed with those 2 hots. That's all it's got to return back to the circuit. That's a scary situation.
It's not ghosts.
Well, it could be. I'm not saying it's not, but it's more likely a problem with your neutral.
Well, so now here's a question for you. Does metal siding have to be bonded?
Depends on what part of the country you're in, I think.
And I remember an inspection I did a while ago where there was an overhead service. The masthead was on the side of the house, and the hot wires actually passed behind the siding. They had sided over it, and it was metal siding. And I mean, just think about the dangers of that. If the siding were to damage the wiring and then you've got these hot wires in contact, I mean, it could energize the whole house, right?
Yeah. I know that I've taken some home inspector training on more like of a national level, and they've talked about the importance of bonding your metal siding. And I've never seen it done in my life. I've never heard of anybody in Minnesota enforcing that. I mean, if it was done, I don't know what it would look like.
I was just trying to picture that. You'd probably have to have an actual bare metal wire connected to all the different components that would be separated and then connected to a ground rod or connected back to the panel somehow. I don't know how you would do that.
I have no idea how you do that. Good question.
I'm sure there's listeners out there who know the answer to this and they can tell us. I'm thinking like probably Charles Buell. He probably knows, right?
Oh, I'm sure.
Shout out to Charles if you're listening.
We got to have him on the podcast sometime.
We should.
Yeah.
That would be fun. Now, I don't understand electrical potential. This, to me, I've read about it, tried to understand it. I can't wrap my head around it. Call me silly or like just thick-headed, but it's just something that's so hard for me to wrap my head around.
Well, that sounds like a wrap, Bill.
Where do we go from here? I've bared my soul about electricity. Awesome.
You know what, Bill? I would need to Google that. Here it is. So the electrical potential, the amount of work needed to move a unit charge from a reference point to a specific point against an electric field.
Oh, that clears it up.
Typically, the reference point is Earth, although any point beyond the influence of the electrical field charge can be used. Yeah, that clears mud, right?
If I was going to sum it up, I mean, this is, I think, what my high school physics teacher may have taught me. I think it's the ability to do work.
Wow, I am impressed you remember that from high school physics, Reuben.
I had a good physics teacher. He was awesome.
You also remember every single thing that you've ever read or listened to. So.
I have forgotten way more than I've ever learned.
Ladies and gentlemen, that is not true. And so whatever he says, we call him something else. But
can we say that on air? Do people know that we call you the savant?
Nobody's ever called me that.
Only everybody who works here does.
Yes.
So.
We
all right. Well, I'm off the hook because apparently electrical potential is more complicated than just the simple explanation. So.
And by the way, as long as I mentioned my high school physics teacher, I should just put a shout out. It was Mr. Ruzek there.
Wow.
That's who it was. Awesome.
Do you think he's still teaching?
Pretty sure. I don't know what else he'd be doing. He enjoyed his work. He had fun doing it.
Well, the only reason I ask is you're like 72 years old and
hopefully he's retired.
Well, how do you guys feel? This was a more technical conversation. I see a more pep in your step, in your voices today.
Oh, for sure. We might have to get electrical expert on our next show to set the record straight on some of this.
Yeah.
Maybe. I think we got at least 95% of this right, Tess.
Yeah. And if not, I am ashamed because I was just teaching this to our trainees on Monday. So my apologies.
I'd say for the part that we need to know as home inspectors, you got it all 100% correct.
There we go. Yeah.
I'm confident of that.
Yeah.
Close enough.
Yeah.
Close enough. 220, 221, whatever it takes.
Whatever it takes. That's right.
Thank you, everybody. You've been listening to Structure Talk, a Structure Tech presentation. My name is Bill Ulrich alongside Tessa Murray and Reuben Saltzman. Thank you very much for listening, and we will catch you next time.
For more information on how we can provide you with the right information about your home before you buy or sell, contact us at structuretech.com.